Looks like we're getting slowly the last of our invitees in. All right, team, let's get the show on the road. So as mentioned before, my name is Jordan. I work as part of the communications team here at UKPN, where I help support our project managers working in the innovation team, which today are Ben and Shuza. You guys are all here to listen to either all of the projects or one of the 4 projects, those being Shared, Hot Chips, Conductor, and Super Duper, all which were part of round 4 of the discovery phase funding handed out by UKRI and Ofgem as part of the Strategic Innovation Fund. So without further ado, I'll hand it over to Sherza, where she will kick things off with Project Shared alongside her fellow presenters. Thank you.
Hi everyone. Yeah, so as Jordan mentioned, I'm Saoirse Lowe. I was a project manager for Shared from UK Power Networks, and also 2 other projects as well that we're presenting. So you might actually have to hear a lot from me today. So your patience is very much appreciated. So Shared stands for Smart Hydrogen and Resilient Energy Decarbonisation, and this came under Challenge 3 of Round 4, which is all about embedding resilience, in particularly looking at decarbonisation of rural communities. I'm also joined by representatives from our project partners, Catherine Sage from Centre for Sustainable Energy, Anthony Reid from Fraser Nash, and Amy Hedger from The First Element, who I'll be passing over to take you through all of the great work that they undertook. I'll firstly start by touching on the problem. If we could go to the next slide, please, Jordan. So due to the kind of topology of the network that supplies them, rural communities can disproportionately suffer from interruptions to their supply, meaning that they can fall into what Ofgem deems a worst served customer category. And they can also see a greater impact from these interruptions, as a result of the surrounding geography, support, and just getting them back on supply can take longer to arrive, etc. And additionally, due to the nature of those rural distribution networks, which are often long-distance overhead lines, traditional reinforcement and resilience improvements can be expensive, and they can also take time to deliver just due to consenting and legal considerations, etc. And therefore, a solution to improve network performance more quickly is essential. I should also add that interruptions to supply can also disproportionately impact vulnerable customers, as they may have a higher reliance on electricity, for example, for medical equipment, etc. I'll now hand over to Amy from The First Element, who's going to talk a little bit more about the proposed solution.
Thank you, Saoirse. So The First Element have been developing a distributed, small-scale, self-generating hydrogen generation and storage device using an internal electrolyser and inputs of water and renewable electricity. The device itself is IoT connected. It's a smart device that can be remotely controlled so that we can be back online in a matter of seconds. The key benefits of this system over potentially using a diesel generator are that it is non-polluting and doesn't have the kind of noise and disturbance associated with a diesel generator. Because it can be back online so quickly, effectively as UPS, it's reducing customer interruptions and minutes lost, and thereby improving the quality of life for those customers that Saoirse has mentioned. Handing over now to Kathy at CSE.
Thank you. So yeah, Saoirse mentioned around the priority consumers. So our main aim was to identify these consumers and assess them, so those most at risk during outages. So we focus mainly on UKPN's priority services register data and some other data sets such as disability data from the census and disability benefits data. And we also included some socioeconomic indicators like fuel poverty and low income. So we kind of created these 4 categories that you can see on the left. So medical dependency on electricity, that's things like if you have a ventilator or a nebulizer or a dialysis machine. Medical reliance on electricity is those things, but as well as having a stair lift or medicine refrigeration. We had intervention impact, so you may find the experience of an outage confusing or distressing. So, for example, dementia or blindness or physical impairments. And then we also had this category for duration sensitivity. So, for example, if it's a longer duration outage, medicine refrigeration becomes more important. So we weighted these variables based on the importance. So we scored higher medical dependency over, for example, low-income households. And then the map on the right-hand side shows some of these scores mapped out. So the PSR data came to us at lower super output area, LSOA, and then that aligned with the census data and fuel poverty. We filtered out urban areas to focus on the rural areas, and then those scores were combined with the network resilience risk score that you'll hear about next from Fraser Nash. So in the map, you'll see the dark purple areas are indicating high scores for consumer priority. The light purple are low scores, and the gaps are the urban areas. Next slide, please. We also did some stakeholder engagement mapping through a workshop and generated a targeted stakeholder engagement plan for Alpha. In this workshop, we set out what information we wanted to gather from stakeholders and mapped out 14 sort of stakeholders on an interest influence matrix. So we covered who we would like to talk to and why, and thought about the relative importance of speaking to different stakeholder groups, and started to think about appropriate methods for how to do this and any potential risks. So at this point, I'll pass over to Anthony at Fraser Nash to talk through their work.
Thanks, Catherine. Next slide, please. So we completed a work package that aimed to indicatively identify rural parts of the UKPN service area that may be considered as being high risk from a resilience perspective. So we did this using a multi-criteria decision analysis, using criteria such as customer minutes lost, customer interruptions, primary feeder length of overhead line, as well as others, and then applied weights to these criteria based on subject matter expert input. As you can see on the left here from this map, we were able to quantify resilience risk for each of the secondary substations in rural areas, and that this map shows you the rural LSOAs with the highest number of substations scoring in the top 10% of overall resilience risk score. Obviously, scoring at the substation level was what the analysis did, but to allow for comparison with the work that CSC did, that Kathy's just explained, we aggregated these to LSOA level. This comparison then allowed us to understand which areas of the network are of most interest in future phases of work based on consumer needs and network risk. So I'll hand over to Amy at TFE to discuss the technology assessment.
Thank you, Anthony. So we designed a system that could be scaled to fit two potential scenarios effectively, one being a 5-home scenario and the other being a 50-home scenario. And we've identified that it would be most cost effective to use kind of a modular approach to this, to scale up and down as required, depending on the siting on the network. Handing back up. Yeah, thank you.
Thanks, Amy. So based on all the findings from previous work packages, we undertook some work to understand how this type of technology may be implemented, initially by identifying key barriers and enablers and undertaking a steeple analysis. Just highlighting the most significant barriers, they included supply chain maturity, availability of a fuel cell, and public perception of hydrogen, although there was some discussion around this, and it was concluded that it was unlikely most customers would be aware of the devices as they're connected further up the network, most likely at secondary substation level. We also undertook a cost benefit analysis, which showed the economic viability of the device varied on a project by project basis, which is based on the cost per customer of any alternative reinforcement project. An extreme example being the solution would be favourable compared to a major multi-million-pound reinforcement project to enhance reliability for, say, just 5 customers. The CBA also highlighted the importance of not oversizing the device, as inefficient design led to lower cost efficiency. So I'll hand back to Saoirse to run through the conclusions.
So as you can tell just from our speakers, it was a really interesting project and a really great proposed solution that we hope to examine more in a future phase. So just kind of to summarize on our key findings, it was of course the identification of those rural locations, also at the substation level, and those consumers as well, which are most likely to benefit from this solution, both in terms of the quality of supply, but then also their experience as well as those stakeholders that we would like to engage in future phases potentially. And then secondly, our findings are showing, as the team have just said, that there wasn't really a one-size-fits-all, and that the solution would definitely require a modular approach, and that feeds into our kind of remaining barrier, which is just firming up that economic viability and also the supply chain maturity as well. But I'll stop there, and thanks all for listening. Back to Jordan.
Thank you very much for that, Saoirse and team. Again, like she mentioned, a really interesting project. And I did forget to mention at the top of the meeting that we will be holding a Q&A at the end once we are done with all the presentations. But also in the meantime, please feel free to use the Q&A feature to drop in your questions should you want to fire them off straight away. But for now, I will hand over to Ben and his fellow presenters presenting hot chips.
Thanks, Jordan. Yeah, hi everyone. If I could go to the next slide. So I'm Ben, I'm an innovation engineer at UK Power Networks and have been working on hot chips with EDF Energy, Northern Power Grid, University of Sheffield and DuPPR, which is part of EDF Group. Joining me today, we've got Umar from EDF and Tom from University of Sheffield. Next slide, please. Oh, we're up to date. Sorry, I'm out of sync there. So yeah, the heating sector in the UK contributes to nearly 1/3 of our annual carbon emissions. And one solution to potentially decarbonising this sector is low carbon district heating. The great thing about district heating is that you can incorporate, multiple waste heat sources to increase efficiencies and create cost savings for customers. We at UK Power Networks, we've always kind of looking into different ways where we can affect this. We've done projects looking at transformer waste heat, sewage waste heat, and now we're looking at data center waste heat, which is another pretty interesting sort of industry that we're thinking about as DNOs across the country. So next slide, please. So yeah, I guess in parallel to the rise of district heat networks popping up everywhere, we've got this influx of data centers appearing across the country. Now, a great deal of the demand of data centers is used for cooling the servers. So, I think ourselves and many others have recognized that these two opportunities can potentially complement one another. And if you look at a sort of map of the UK, there is that sort of complementary sort of look of different sort of data center clusters as well as heat networks sort of overlapping with one another. So that is really kind of where the idea for hot chips was born. Great project name, I will add. And yeah, the whole point of the project really is to address round 4 SIF Challenge 2, which is looking at incorporating greater heat flexibility into the UK's energy system. So we looked at, if we were to develop a district heat network, how would you incorporate waste heat from a data center into that heat network? And then we looked at thermal storage solutions, which then allowed those customers in that heat network to potentially participate in flexibility services, helping to make their bills cheaper, and then also helping to reduce the peak demand for us, the DNO. And I will now pass over to Umar to sort of chat through how we went about investigating this.
Thanks, Ben. So as part of our project, as Ben mentioned, we conducted a market analysis piece focused on understanding data centers and surplus heat recovery. We looked at the 4 main types of data centers, their cooling architectures, and the expected output temperature from each kind of cooling setup. And we found that in most cases, data centers operate well below their maximal utilization capacity, and it's actually around 30%. And despite this, the energy consumption is fairly consistent throughout the year, which means that the heat they produce is also very stable. And this stability makes surplus heat a viable heat source for domestic heating. Next slide, please. So we found some great examples across Europe where this has already been implemented. So for example, in Paris, heat from a data center was used to warm the Olympic swimming pool. And then after the Olympics, the same heat source was then redirected to approximately 1,000 homes in the surrounding area. And in Scandinavia, where the practice is probably even more common, in Sweden, for example, Microsoft supplies 40% of the heat to a network serving 100,000 homes. And in Denmark, Meta run a similar operation in a city called Odense. So I think it demonstrates the real world potential of using data center heat recovery for district heating. Next slide, please. So using our findings from the previous kind of work packages, we developed a high-level modeling tool. So it considers both technical and economic factors of heat recovery. So in terms of operation, users can input details about their specific heat recovery scheme, and the tool calculates potential energy savings, associated costs, and carbon savings as well. So to test it, we created a case study based on real heat network projects from the HNDU pipeline. So for the example that we selected, the annual heat demand was 50 gigawatt hours, which is approximately equivalent to 10,000 homes. A data center with a capacity of 20 megawatts, and the distance to the demand site was 0.5 kilometers. We also used some real anonymized load data from a data center operator to validate our assumptions. And essentially from the model, we found that the example that we selected would be suitable for an in-depth study according to the DESNES methodology, because the linear heat density was above a certain threshold. The heat supplied would also reduce grid energy consumption by up to 65% compared to the counterfactual of using air source heat pumps solely. And on the consumer side, if we assume that we can kind of load shift a third of the peak load, then households can benefit around 54% in heating bills, compared to, again, the counterfactual of air source heat pumps without any flexibility measures in place. And the tool also calculates CapEx, OpEx, and carbon savings alongside that. And I'll hand over to Tom, who will kind of walk you through some of the key findings from our stakeholder discussions.
Thank you, Umar. I hope everyone can hear me. So stakeholder engagement has been central to this work, and I guess we wanted to inform the modelling, firstly, with real data, and secondly, understand how to break down some of those barriers and opportunities we see that are not identified in the literature review. So in work package 3, we sat down with multiple data center operators to understand how they run, how they cool, and whether they join a heat recovery scheme or not. Some things we identified is that cooling is evolving fast. AI workloads are growing, so operators are moving from air cooling to hybrid and, some of them solely liquid cooling. Now, this raises the outlet temperature, good for recovery, but introduces more variable heat profiles across the day. Thus, we need some sort of thermal storage. Attitudes to joining heat network schemes were very positive. Several operators said they provide heat at zero cost if the offtake model is simple and low friction. Their concerns really were practical They want to serve their own customers first, so uptime is very important. They cannot guarantee a perfectly steady heat output. So any network solution must be designed around that reality, most obviously with thermal storage. Some other pieces of information we extracted from our conversations is that the motivation is often strategic and not financial. Heat is the byproduct, so operators just want an easy way to connect and not profit. For the commercial side of things, they wanted a repeatable framework for who funds the CapEx, who holds the variable supply risk, and how to handle VAT and tariffs. And timing. They think there's a sort of a 2-year window where heat zoning legislation is coming into effect. And this creates urgency, and it also means that some of the infrastructure that's going to be built is not locked in first. So there's an opportunity to move here. Could we have the next slide, please? So the opportunity is real, the appetite exists, and the design answer is storage first, and the commercial answer is a standardized commercial framework. In this project, really, we wanted it to open doors for collaboration between DNOs, heat network developers, and data center operators, if we're going to take this forward, sectors that have not often interacted or not interacted as much as they should. So to make waste heat work at scale, we should encourage these sort of conversations at the design stage, quantify the recoverable heat, size thermal storage appropriately, and keep energy costs fair for consumers. And through Hot Chips, we've set a high-level roadmap and built a preliminary tool to start to do this and understand this so that these stakeholders can potentially progress some pilot and demonstrator projects in the future. So we'd recommend standardizing a heat recovery scheme, clear CapEx recovery models, explicit risk allocation for the variable supply aspect, simple VAT and pricing options, and a template both for air and liquid cooled sites, and storage specifications size to this AI variability. In short, we want to align partners, lock in commercial template, size storage for AI, and move while this policy window is open and this infrastructure is not already locked in. We see this as urgent due to new heat zoning legislation coming in. And I'll pass you back to Ben.
Nothing more for me to add, but yeah, back to you, Jordan.
Thank you very much, Tom, Umar, and Ben, for your presentation on Hot Chips. Again, I'll hand the mic back over to Shirsa, where she will be presenting Conductor.
Hi guys, yes, so back to me again, as I was also project manager for Conductor, which this time was around Challenge 1, which was looking at novel methods to increase capacity from existing assets. So I'm joined by our project partners. We have David Wyatt from Energy Systems Catapult, Leo Murray from Riding Sunbeams, and Jean Bétienne from Enerail, which is a spin out as part of University of Birmingham. If we could have the next slide, please, Jordan. So this project looked at specifically traction bulk supply points, or TBSPs, which are essentially large capacity network connections, which are designed to support peak demand on rail traction systems. And because traction power is typically very peaky in nature, coming from trains, passing through, etc., this capacity is typically not optimally utilised. There's around 20 TBSPs in UKPN's area, which connect to Network Rail's DC traction system in its southern region, which overlaps with our SPN license area. And this region is the densest part of Great Britain's electric rail network, consuming around 1/3 of all traction electricity, which is used by Network Rail. And some of these connection agreements are actually up to 70 years old, and so they naturally only support one-way demand, meaning they currently prevent export from non-traction sources. If we could go to the next slide, please. So Conductor aimed to investigate the potential for adding battery energy storage systems, or BESS, to these TBSPs in our license area, which again connects to the DC traction network. and allow them to potentially participate in flexibility markets. As one of the UK's largest electricity consumers, railway participation in flexibility could offer significant benefits and address that challenge of transforming currently non-flexible demand into something dispatchable and dynamic. BESS could obviously minimise some of those peaks and troughs from that rapidly changing traction demand. And typically, rail corridors can, connect urban centres which have higher demand, but they also might have adjacent land available which could host some of those units. I should add that Network Rail were not a formal project partner on this project, but we did engage, the project team engaged with a dedicated point of contact and various different stakeholders throughout discovery. But I'll now pass on to David.
Thank you very much. One of our contributions to this project was to assess the ways in which energy storage systems, or ESSs, have been deployed in rail applications worldwide. In our review, we identified 65 projects, which we categorised against the 5 dimensions on the slide. The vast majority of projects were on light rail systems, in other words, metros and trams, normally on DC power systems, and were often used as their primary use case to support regenerative braking, since, as Saoirse mentioned, some DC systems lack the capability to export power. This is one of the reasons that supercapacitors dominate in terms of technology, although batteries are used for longer duration applications such as backup power. Only one system that we found had grid services as its primary function, and we didn't find any examples of projects equivalent to Conductor across all 5 dimensions, the green outline I've shown on the slide, demonstrating that this is an innovative area to explore. I'll now hand over to Leah. Thank you.
Thanks, David. So we led on the stakeholder engagement piece to this project, and as you can see on the slide, Network Rail is a very large organisation, about 40,000 people work there, and it is split up. It's heavily devolved on a geographical regional basis, but it is also there's kind of verticals within the business as well, and each of those acts with some autonomy. So you can see we've exploded Network Rail out into a lot of different bits with varying levels of importance to this. Pretty much everybody that you see on the slide we spoke to over the course of this project. So we were trying to understand both whether and to what extent there is any energy storage already integrated on British Railways, and effectively the answer is no, there isn't. There's onboard storage, as David says, but there's no actual operating wayside energy storage integration at all on the network. There are some projects within Network Rail that are looking at this, but not in the way that this project has explored. So there's specifically smaller things which would be looking at traction power operations. Over the course of this engagement, what we were trying to do was understand whether there were railway problems that we could solve at the same time as providing the benefits to the grid. That is the premise for this project. And the upshot of that was that not where we were looking is the short answer. So we were looking at the southern region, which is a DC electrified railway network. The architecture of that system means it actually doesn't lend itself very well to providing both operations, traction power operations to the railway and services to the grid. But we also found that there are some major techno-regulatory challenges around integrating storage that is capable of interacting with the grid as well as providing useful services to the railway. So these, I can summarize these as effectively, there's a bit of a fundamental incompatibility between the regulatory requirements of generators that are connected to the grid, and of course that battery energy storage or energy storage of any sort is classed as a generator, and the protection philosophy that operates on the railway. So there are requirements of you as a generator that can't be met under the current protection arrangements on the railway. Now, this actually probably doesn't really apply too much to the southern region itself, but most of the network outside of the southern region is electrified in a different way. So one of the upshots of this project is that we've got the relative the stakeholders speaking to each other. So NESO is now in direct contact with the key technical personnel at Network Rail to bottom this issue out and hopefully come up with some remedies to this incompatibility. But yes, fundamentally, we couldn't find railway problems that we could solve with battery energy storage at the same time as providing network benefits, not in the places that we were looking. And I think I'll come back to what else might be possible in the conclusion slide. That is me. So I will pass over to you, Zhongbai, I think.
Thank you, Leo. Next slide, please. So my team has investigated the technical option engineering. So we have modeled the railway power systems, and here we have identified two options for this energy storage renewable connection. So with railway network. So on the left-hand side, we connected the energy storage directly to the DC networks. And on the right-hand side, we connect using AC with AC-DC converters. For the DC connection, is kind of a simple and inexpensive infrastructure upgrade. So we can use some mature DC-DC converters to connect energy storage with railway. And there are some challenges for this topology, because one way is simple and inexpensive, because we can engage the trains, operation, traction, or regenerative braking, with energy storage directly, and then the surplus regen power from the trains can be used to charge the DC connected energy storage directly. And when there is a higher traction demand, the energy storage from DC bus can discharge and support this peak demand directly, and it gives a good enhancement of the railway network energy efficiency, and can also remove the peak demand and increase the railway capacity a little bit, but it also limits the control flexibility. So because of the existing single directional rectifier, which connect with the grid and the main supply point to the DC railway. So this converter doesn't allow the feedback from the DC railway network back to the grid, which cause less flexibility and less engagement between the grid side and the railway side. So in the other way, the AC connections on the right-hand side can overcome this drawback, because this energy storage and renewable directly connect to the three-phase connection point, and then the energy storage can engage with the grid side and railway side. But the drawback is higher investment cost occurs, because we're gonna update the existing railway traction converter, rectifier, to a bidirectional converter to enable this bidirectional power supply from the trains to energy storage. And but there is a good evidence that both the grid side and railway side can be better controlled by this large scale energy storage and renewable. So we can both increase and energy efficiency and also increase the flexibility. Okay, thank you. Next slide, and I will hand it over to Dave.
Thank you, Zhongbai. As our other major contribution to the project, we assessed the benefits and costs that the conductor concept will bring to different parties in the system. Firstly, installing batteries, of course, potentially reduces peak demand, allowing deferral of reinforcement, or alternatively greater capacity for new connections on existing substations. This would be achieved through the batteries participating in flex services for the distribution system operator. Secondly, Network Rail could reduce its liability for use of system charges by accessing stored energy in the battery through a power purchase agreement with the battery operator. And finally, wider society would benefit from reduced carbon emissions through two routes: reduced renewables curtailment through use of the battery to store the renewable output, and reduced emissions associated with network reinforcement works. As an indicative value, installing battery energy storage systems at third rail traction sites in areas that require flexibility in 2050 could contribute somewhere between 4 to 7% of the total installed battery capacity forecast in that region. Leo will now present some conclusions.
Thanks, David. So, I spoke about the techno-regulatory barriers, which were not known prior to this project. So, it was a classic discovery project. We've definitely discovered something useful there, particularly as the railways have ambitions to host quite a lot of embedded generation on their own systems. And if export is impossible, either from BESS or from embedded generation behind the meter on their networks, that is going to curtail those ambitions. So it's useful that we've understood and characterized the challenges there. The rollout of battery electric trains, which is expected to be the new paradigm for rail decarbonisation in the UK. We've been very slow to put up overhead lines. Only 38% of the network is electrified at the moment, maybe 39% as of this year. Not enough to meet decarbonisation targets. So battery trains will be a solution in lots of places. That could add some flexibility to rail traction demand in the future. It's the reason why this project hit a brick wall, in fact, was that I think we looked in the wrong place. Essentially, we focused on the southern region. It's where we've done quite a lot of work in the past. And we know that battery storage will be useful on the traction power system in the southern region to support more embedded generation. But it's not where the network needed flexibility. So none of the traction bulk supply points on the southern region of Network Rail's network are in places where UKPN required flexibility. So I think one of the key things that we learned from speaking with railway stakeholders is that of the various different types of use case that energy storage could perform on an electrified railway, by far the most valuable railway use case is enhancing capacity on an underpowered route so that more train paths can be added. Now, we weren't looking in the right place for that because the southern region is not it's not expanding. There's no plans to add lots of services, whereas in other parts of the country, we're electrifying freight. Freight trains draw an enormous amount of power, and some of the key freight corridors that connect to ports in the UK are currently underpowered for the trains that have actually already been ordered by freight operating companies in order to achieve the getting the diesel only trains off the network by 2040. So we're hopeful. We're meeting with other Network Rail stakeholder system operator to find out more about Network Rail's contemporary thinking about how they're going to meet these additional power challenges, and potentially to look at whether battery energy storage at a bulk supply point that is supplying one of those freight corridors could be used as an alternative to a traditional power supply upgrade, because those are phenomenally expensive, and it's mostly a voltage regulation challenge actually, and battery energy storage could potentially do that much more cheaply, and we could probably fold in a renewable energy feed at the same time without having to add that generation to a connection queue when the queue reopens. So meanwhile, NESO is talking to the key technical personnel at Network Rail about this export challenge. So I think we've got some very useful outcomes from the project, even though we weren't able to find a a viable use case for battery energy storage on the southern region. And I think that is me. So, Saoirse?
Yeah, all good. We can pass back to Jordan.
Great.
Thanks.
Yeah, thank you very much for that, team. We'll now move back to Saoirse for the last project, Super DuPPR.
We can go to the next slide, please. Okay, great. Yeah. So back to me, the final one, I promise, which is Super DuPPR, which is actually the project name. And I've now had the pleasure of introducing such a great name in various different forums now. It actually stands for Dual Purpose Power Reserves, and also came under Challenge 1 for round 4 of unlocking capacity for existing assets. And I'm joined by Anna and James from the Met Office. We could just go to the next slide, please. So just to introduce the project, as we're all aware, electricity demand is set to increase due to electrification, and a key focus of distribution networks is obviously the management of peak load, particularly during the winter, and that's obviously, of course, when solar generation might be a little bit lower. So operators of critical infrastructure, for example, telecoms, they have a reverse problem. So they need to keep their assets cool during summer, and they have reserve power systems installed to maintain their operations in the event of a power failure or interruption. And historically, this backup generation has been powered by non-renewables, such as diesel generators, but it is expected that these operators will look to low carbon technologies to replace these as they transition. If we could go to the next slide, please. So as national infrastructure operators, BT or British Telecoms, they have thousands of potential sites that could decarbonise and represent some of this opportunity. So BT were not a formal project partner on this discovery, but we had dedicated points of contact throughout. And as a result of this, our analysis focused on 3 main kind of asset classes of theirs, which included data centres and something called metro nodes, and tier 1 assets are essentially a type of router. And our discovery essentially aimed to understand if these types of assets are suitable for dual purpose, so that resilience, but also flexibility. But I'll now hand over to Anna to talk a little bit more how we did this.
Okay, great. Thanks, Saoirse. Next slide, please. Thank you. So the first thing we did for the project was to develop a series of weather-dependent electricity load models for each of the assets that Saoirse just mentioned. This involved initially comparing the demand and temperature profiles for each site, just to check that there was actually a correlation between the temperature and the demand, and we could then identify which assets had a very strong temperature influence on their demand. The next step was then to generate a GAM model, which would then predict the energy demand. And in each case, this GAM model was trained on 3 input predictor terms, and these were the day of the week, the hour of the day, and temperature, as these were the variables that we identified as having the biggest influence on the demand. The model was then used to produce a predicted load time series for the same period over which we had actual demand data, so that we could compare the two. And the results of this are shown in that last figure on the slide. And you can see that actually the model did produce a very realistic demand profile, which closely matched the observed demand. So we can have fairly high confidence that our model is doing the right thing and is giving a very realistic result. So next slide, please. So in order to then assess the capacity at these sites, we fed 50 years of weather data into the GAM models in order to create an extended time series or climatology of the plausible maximum load, and therefore the reserve capacity available at each site. But there is a fixed capacity of reserve power that is built in to each site in order to meet backup requirements for critical infrastructure, in particular in the summer when the cooling demand is really high. But in winter, when that cooling demand is much lower, we then have shown that actually the requirements for reserve are much lower. And so there is actually surplus capacity at each site. This allows that some of the capacity could actually be used for other purposes. So in this case, flexibility. We showed through the analysis that the larger sites, so the data centers and the metro nodes, were actually capable of providing reliable flexibility throughout most of the year, outside of those much warmer summer months when the reserve capacity is needed for cooling. But outside of that, the reserve capacity is actually surplus and could be used for flexibility. And then next slide, please. One thing that we did find, however, was that not all of the sites would be appropriate to use for flexibility. So the smaller tier 1 sites that Saoirse mentioned at the beginning did not have a strong connection between temperature and the demand at the site. And there was a lack of a seasonal trend within the data. And this then led to there being no extended periods across the year when there was actually surplus capacity available at these sites. And so these much smaller sites would not be suitable for using for the flexibility services. And I'll pass over to James now.
Thanks, Anna. Sorry, I think we've gone to the wrong slide there. The next one again. Okay, great, thanks. So the final work package, we took all of the results from the previous work packages, so understanding this surplus capacity, how much of it exists at different sites, and showing that it exists during the winter for this infrastructure, which is really sensitive to its cooling demand. So now that we knew that that surplus capacity is there and could be used, we wanted to understand what the value of it is. And we did this for UKPN's LTSU and SAOU flexibility products, which are aligned with similar products offered across the country by other DNOs. The results showed that there was very high value in some regions, and that this was rapidly increasing over the coming winters due to the increasing need for flexibility in UKPN's constraint zones. But this value wasn't evenly distributed, so there's a bit of a postcode lottery going on. In follow-up workshops that we held with BT for this case study, this was identified as a real challenge for them. Both the sensitivity to location and just the rapid change over time and the uncertainty associated with that. So that was identified as a barrier for them to engage in this alongside other challenges, which included their security approach and risk, just their general risk aversion, having to align everything. In the case of the Metronode A, we have shown the results here for a 1 megawatt size data center or Metronode A, and it can earn towards £400,000 a year for this size of assets, which is very high in the best case, but that is only in a very small number of constraint zones. So most of us would be lower value than this, but still the majority of assets exceeding £10,000 per financial year. Next slide. So wrapping up all of the work packages, we demonstrated that these reserve power systems installed for critical infrastructure like with BT or potentially other use cases, other data centers or hospitals or infrastructure, there is this potential in some but not all of the assets to operate surplus capacity for flexibility products like LTSU and SAOU, and potentially high value in some of these zones but not all of them. So a challenge moving forwards is to identify how to make this either financially viable or to engage with policymakers to try and support this to be implemented where it has the most value to the grid and to the DNOs, even when there are these challenges for engagement. Thank you very much.
Thanks for wrapping us up. Excuse me. Thank you for wrapping us up there, James. Also to Anna for presenting, as well as Saoirse, as you would have seen, has had a long old past hour. As mentioned at the top of this meeting, we do have a Q&A function. So for anybody that would like to leave any questions to all of our project partners and project managers across the 4 different projects you've heard from today, please do so now. But yeah, thank you very much for joining us. Thank you for everybody. Thank you to every one of our partners, as well as my colleagues Saoirse and Ben for presenting today. And yeah, have a good one.
Should we just make sure we've answered a few of these questions?
Yeah, if we'd like to work through them, we can do that as well.
Yeah, I guess to kick things off for the shared team. So the efficiency levels possible from the HT unit. I can see that that's kind of been answered in the Q&A there, but I don't know if anyone has any thoughts to add to this point. No, next one. Did you study a specific hardware, or was it a generic hydrogen fuel cell? Again, I think we've got an answer here.
Yeah, I think our next one is from you, Ben.
Yeah.
On is there scope for regen braking in battery electric trains? Maybe Leo is the best to call on you on that for in relation to our project.
Yes, I mean, regen braking is pretty much ubiquitous now across all of the electrified rail network, one way or another, right? Even when there's no storage on the train. But it's often wasted because unless there is another train available in the same electrical section to pick up the regen braking, then there isn't anywhere for it to go, and so it gets burned off in resistors on the trains. So one of the key use cases for wayside energy storage is to support making better use of regen braking. So that would be one of the key components of an investment case for integrating energy storage on a traction system. And Jean-Bert, I can see he's taking his mic off because, you know, you did a piece of work looking at Merseyrail, didn't you?
Yeah, and yes, so Leo has answered the wayside, so batteries, which can be good to collect regen braking power from trains. And if you mention, so Ben, if you mean the battery electric trains, so this battery can be onboard battery. So there are increasing number of battery EMUs so in the UK, and for these battery trains, the onboard battery can collect the regen braking directly. But this also relies on some smart energy management systems. So because you may need to manage. So when your train is braking, so you have surplus power capacity on the battery. Yeah, I think so. We have answered this question.
Yeah, thanks, guys. I'll skip my next question. We'll go to Michael's. So if exporting power back is a regulation challenge, which may take years to address, would having two different commercial models be an option? For an example, solar and battery energy storage, providing rail-only services owned by Northern Rail, or solar and battery energy storage next to the traction BSP exporting is third party.
Yeah, the answer is yes, but I think it doesn't give you much of an advantage over the business as usual. That's the problem here, because you know, in the real world, battery energy storage has to be able to revenue stack, right? It's got to be able to do different things in order to underwrite the investment. And what we were hoping to do with the Conductor project was find ways to provide value to both the rail side and the network side. And so, you know, solar plus BESS, providing the rail only services that is behind the meter on the traction power system, is something that we know Network Rail quite wants, right? You know, they've asked us about this a lot in market engagement around their solar plans, but that battery energy storage is very unlikely to be able to wash its own face if the only thing that it is doing is load shifting renewables. Maybe if it can provide some traction power operations, but like I say, there's no precedent. So there's no actual examples of integrated wayside energy storage on the system now. And then if we can't access any revenue streams from providing services to the grid, it's really hard to make the numbers work. And then on the other side, if you're not installing your solar and your BESS behind the meter, you don't get the advantage of not having to join a connection queue and, you know, get into the mess of you know, being in the mix with everybody else, which is one of the things that's really helpful about just supplying a railway directly, because you don't have to worry about those things. So in principle, the answer is yes, Mike. You know, yeah, that those things would work in theory, but they might not actually pencil out commercially. I hope that's answered the question.
Sounds good. Should we move on to, I think there's one around from David. Yeah, on Super Duper, which is, are operators willing to use their reserve capacity for flexibility services given they will drain the batteries and thus no longer be available to provide reserve power? So a sort of backup assumption was made in the calculations, but I'll let Anna or James maybe take that on how we kind of work that out so that nobody would be left with nothing.
Anna, feel free to jump in as well, but I've just written a short response as well to David. So this is a really good point, and it's something that we've been really keen to try and communicate from our results, that this surplus capacity is something that can be used without incurring risk to the asset owners. So in the case of BT and other cooling-driven infrastructure, their energy use peaks in the summer, responding to high temperatures. But that means for most of the rest of the year, and especially in winter, there's a guaranteed baseline of reserve power that is higher than needed, so that could be used for other purposes without incurring any additional risk. So in a way, the current approach is maybe not very sensible risk management, in that the risk is concentrated around the summer. So yeah, that was the sort of one of the key themes we were trying to communicate. This is a win-win. It's you're able to generate this new revenue stream from something that's currently not being used. Most of this reserve power is currently coming from diesel generators, but as part of meeting decarbonisation targets and also switching to cleaner technologies that don't pollute urban centres, a lot of companies are beginning to look at lithium-ion batteries, and if they want to do this, having these additional revenue streams is going to be really vital.
I think that might be time. I guess thanks everyone for joining. We'll really good to sort of share some of the projects. I guess everyone have a good rest of your day, and yeah, look out for more stuff that UKPN are doing in the innovation space in the future. Thanks very much to all the presenters.
Thanks guys, and for all the great work as well. It's been a pleasure.
Thanks,
and to Jordan.
Thank you.
Thank you.
Thanks guys. Bye bye.
Thank you. Bye.